Welcome to Physics 142 Online. I'd like to work out an example problem that actually comes from your homework assignment. It's a problem that is nice because it reviews some of the concepts that you learned when you were studying collisions in the first semester of the course, and then makes use of some of the concepts involving harmonic motion. So first, let's take a look at the problem, and then I'll draw a sketch and solve it, or at least part of it. At first it says a block of mass m is on a frictionless horizontal surface and is attached to a spring of spring constant k as shown in the figure. Well, I decided that I would sketch the figure here on my sketch pad. So there's a wall, and then there's a large block of mass m, capital M, sitting on this horizontal frictionless surface, and here's the spring with spring constant k. I usually use a cursive k for this just out of habit. And then it says that a bullet of mass little m is going to strike the block. It's coming in from the left. It's going to strike the block, and it has an initial speed v0. And when it strikes the block, it is going to embed itself inside the block. The bullet has mass little m. And this problem is purely a symbolic problem, one in which there are no numbers involved, so it's great practice at teaching you how to work problems symbolically. Remember, as I've said in class, when you have a problem that gives you the answers, it says something like, show that this is the result. You shouldn't look at the result until you're done with the problem. The result is only provided to give you a way to check your answer after you've done it. But staring at the answer is not going to help you get the answer. So, this problem involves a collision. And you probably should remember what kind of a collision this is when two objects collide and stick together, and therefore travel together after the collision. That's called a perfectly inelastic collision. And in order to find the speed of the block and the bullet immediately after the collision, we have to use the principle of conservation of momentum. Because no matter whether the collision between two objects is elastic or inelastic, or the special case of perfectly inelastic collisions where they stick together, no matter, as long as the net force acting on the two masses, or you could have more than two masses, but in this case, two masses. As long as the net force acting on the system is equal to 0, then we have momentum conserved. So, let's just remind ourselves where the equation comes from. It comes from the principle of the conservation of momentum. And applied to this one-dimensional system, we take all of the momentum components in the x direction. We will call the horizontal direction the x direction, positive to the right. We add up all of those x components of momentum initial before the collision, and we set them equal to the sum of all of the x components of momentum after the collision, or final. That is a simple mathematical statement of the law of conservation of momentum. And this is very easy because the only object that has any momentum in this two-mass system before the collision is the bullet. So that's m v0. And the block of mass big M is not moving. And afterwards, after the collision, they stick together. And so what we really have is a combined mass moving off with some speed v. And that's what we're trying to solve for in part A of the problem. So it's the combined mass, little m plus big M, and it's the speed v with which they travel together. And that's all we're trying to solve for. So let's just solve for v, and we get that v, if we divide both sides by little m plus big M, we get m v0 divided by the sum, little m plus big M. In solving problems like this, be careful when you've got two different symbols for masses that you do your best to try to distinguish them. So little m and big M, I've tried to show that they're different from each other. Sometimes when we get in a hurry and we scribble these things down, we're not real careful about it, and then that makes things problematic, because sometimes we might think that those two m's are the same and add them up and get 2m, but that would be a mistake. So simply by applying the law of conservation of momentum, we have found the initial speed that the two mass system has right after the collision. So then what we've really got, and I'll just go ahead and draw another sketch just to make it clear, is just after the collision, and this happens so quickly because the bullet embeds itself inside the block. So we've got the block of mass big M and the bullet of mass little m, but they're connected to the spring, and because of this collision, they actually begin to move with this speed v before the spring is even compressed. At least that's our approximation. This collision happens so quickly, they begin to move even before the spring is compressed at all. And so now we want to find the amplitude of the subsequent motion of the system. The mass is going to oscillate back and forth as the spring is compressed and then stretched because there's no friction on this surface. And the key insight for part B, what we did up here was part A. Now for part B, the key insight is to think about this velocity and ask ourselves, well, what is that? How is that related to simple harmonic motion? And for simple harmonic motion of a mass spring system, I will just remind you that the general expression for x of t is a cosine omega t plus phi, right? And that the derivative of that, which will give us the velocity, would be negative omega a sine of omega t plus phi. All right? And what we have here in the bullet block system, we know what the speed is before the spring is even compressed, and when the spring gets compressed, it will impart a force on the block to the left, which will tend to slow it down, right? So the insight here is that v, which is the velocity we have in the box, is the maximum v of the system, because it's the velocity it has at the equilibrium position. Now compare this to the general expression for v of t, and this term out in front is nothing more than the maximum v, the maximum speed. Sine function goes back and forth from 1 to minus 1. It never gets any larger or smaller than 1 or minus 1, so that the maximum value that v can have is omega times a, right? So this v, the maximum v of the system, is equal to omega times a, and that will allow us to solve for the amplitude a. So let me just rewrite this equation. The left-hand side from the box is mv0 over little m plus big M, and the maximum v of the system, when you have a simple mass spring system, is omega a. Okay, so now we can solve for a. We'll need to find omega in a minute, but I'll go ahead and solve this for a. A is equal to little mv0 over omega times little m plus big M. Now, what is omega? If you have a simple mass spring system, we're used to, if you look this up, you'll see that omega is square root of k over m. But rather than write m, I'm going to write mass. And the reason is this system has the two objects stuck together, moving together. So the total mass of the system is little m plus big M. That is what belongs in the denominator. So omega, in this case, is square root of k over little m plus big M. And that's important. It's easy to make the mistake of just writing it as k over m. Now, we're almost finished. We take this expression for omega and we plug it in to the denominator. which will give us the expression for the amplitude. And I'll just, since we're almost done solving this, I'll put a therefore A is equal to, the numerator is mv0, the denominator is square root of k over little m plus big M times little m plus big M. And this would not be wrong to leave it like this, but it's not simplified because we have little m plus big M inside the square root as well as outside the square root. So let me take care of the fraction in the denominator. So the 1 over square root of m plus m ends up in the numerator. The m plus m ends up in the numerator. So we have square root of little m plus big M times m v0 over square root of k times little m plus big M. And now we can see how to simplify. The square root of something over that something reduces to 1 over the square root. So a little simple arithmetic gives us square root, in the denominator, square root of k times square root of a little m plus big M. And when we multiply two quantities inside square roots, we can just write the square root over the product. So we get mv0 over square root of k times little m plus big M, all inside the square root. And sure enough, that's exactly what the question statement told us we should get if we did the problem correctly. The problem statement goes on to say find an expression for the position x of the block as a function of time. That's actually pretty easy because now here's the expression for x, the general simple harmonic motion expression. We know a. The only thing left, and we know omega, the only thing left for us to do is to find phi. And again, that would require using the initial condition that at time t equals 0, the velocity is equal to v max, the omega times a. And so if you do that, you'll be able to find the phase constant phi that goes into the original equation for x of t. I won't do that here. I'll let you finish that for practice. But this problem is essentially finished. To recapitulate here, we apply the law of conservation of momentum to find the velocity of the system after the collision. That, then we realized, was the maximum velocity for this object in simple harmonic motion, which allowed us to solve for the amplitude A. I will see you in class.